So in this installment, we're going to start looking at individual types of forces that have names. And visually, what we have at the beginning of this unit, we laid out this concept map. And so here we are with forces, and we are looking at the first of them. In the next series, we will increasingly look at a number of other forces. Now, really, we should view this force and call it gravity. And we should now, as respectable physicists, strike the word weight from our vocabulary. It's not a word we should ever use again because it's confusing. It's used in colloquial usage, and it's used interchangeably to mean the force of gravity and the mass. We use it interchangeably, and we'll see why that is in a moment. In short, weight is the force of gravity. It's not mass. They're completely separate from each other. So we may do a little diversion here for a second and take a look at the definition of force. If you look up force in a regular dictionary in general usage, it will say the strength or energy. Force is energy. Exerted or brought to bear, the cause of motion or change, or active power. Now, in physics, power is a separate concept, as different from force as velocity is from time. They are completely different from each other, and they have very little relationship to each other. Force is also not energy. It is also not the strength. And so this entire colloquial usage of the word force is terrible, and we shouldn't. So now, getting more closely, the technical definition is something much more like an interaction. And we know that there are 4 or maybe 5 fundamental interactions that, when unopposed, that means unbalanced, will change the motion. And changing motion means momentum of the object. So this is the useful way we want to think of force. Or we can just simply think of it as anything that will bring about a rate of change of momentum. So let's take a look at a few constants here to help clarify what I meant by not using weight. In simple terms, force in the English system and in the SI or the metric system force here. Force in the English system has units of pounds. And the SI system, it has units of newtons. And that's something, until you learned about momentum, you'd probably never heard of newtons before. The unit of mass in the SI system is kilograms. And in the English system, it's slugs, something you have not heard of before. So it just so happens that people erroneously use these terms kind of interchangeably on Earth. Kilogram is mass, which is the amount of matter. Pounds is a force, and forces bring about accelerations. Newtons is a force that brings about accelerations. So how is it that we sometimes use these interchangeably? Well, it turns out that we can convert them between each other on Earth at sea level. And that conversion is roughly like this. 1 pound is about 0.45 kilograms, or it's about half a kilogram. 1 pound is about half a kilogram. 1 kilogram is 2.204 this many pounds. In other words, 1 kilogram is about 2.2 pounds, or about 2 pounds. But that is a conversion that we can only use at Earth at sea level. And, by another comparison, gravity, which we've known for quite a while, the acceleration caused by gravity is this number. It could be variously used as these. In the English system, it's 32 feet per second squared, or this feet per second squared, which you haven't seen. When I first started learning physics in 8th grade, when I was in school, we actually learned this and used it, 32 feet per second squared. So this idea here, the force of gravity, how we calculate it is we take the mass and multiply it by the gravitational field strength. also known as the acceleration caused by gravity. Now, this little letter g, it turns out, depends on other factors, which we'll study in more detail, but this is the big M is the mass of the subject body. So if we're thinking about us living in the vicinity of Earth, it would be Earth. And this R is the distance betwixt the centers of masses of the body. So that means center of the Earth to center of the person. That is R. Not the distance between their touching surfaces, but the distances between their centers of masses. All right, so Fg is a force, and I don't want to use the W word, but the W word means force. SI unit newtons, imperial unit pounds. It is the force of gravity on a body toward and from. It's that mutual force. The gravitational field strength on Earth is 10 meters per second squared. On the moon, it's 1.6. On Mars, it's 3.7. So the formula for the force of gravity, is the force of gravity is the mass times the gravitational field strength, which you can see comes right from F equals ma. Now, even if we have an object that's on a table, like so, and we go to determine the force of gravity, it's an acceleration you would observe if the table were slipped out of the way. So if we push that table out of the way quickly, we would experience that acceleration. Well, that gravitational field strength, how strong gravity is at this point in space, is there whether or not the table is there. So that acceleration is a way to measure how strong the gravity is if it were not being supported and were allowed to free fall. So let's just do a quick calculation here. We have, we want to know the weight or the force of gravity of a 165-pound astronaut in newtons at the surface of the Earth and on the moon. So we have 165 pounds at the surface of the Earth, and we know that if we want to express this in kilograms, we need to get rid of pounds. And our conversion is kilograms to pound. 1 kilogram is 2.20. And doing the dimensional analysis, we're left with 16.5 divided by 165 divided by 2.2. Which is 75.0 perfectly. So it's 75.0 kilograms. And if we want to know the force of gravity on Earth, then with mass times the gravitational field strength, we have 75.0 times 9.80665. Which is 735.4988 newtons. And we had 3 significant digits here, 3 significant digits here, 3 significant digits here, and plenty more here. So we would say that the force of gravity the force of gravity between the astronaut and the Earth is 735 newtons. If we were to do that on the moon, force of gravity on the moon, well, that would be mg again, 75.0, but now it's 1.6. And that is 120 even. Three digits. So a person on Earth, this could be any of you who happen to be about 165 pounds, would have a weight here on Earth, or the force of gravitational attraction of 735 newtons. Transported to the moon, your force of attraction would only be 120 newtons. And that's what weight is, the force of gravity is, and how we can calculate it simply